Thank you for attending our session. Hi everyone, my name is Hiroshi Suzuki, and this is Minoru Kobayashi. Today we will talk about recovering deleted VSS snapshots and the recovering tool named VSS cover. Let me introduce ourselves first. This is Minoru Kobayashi, who is a forensic investigator. And my name is Hiroshi Suzuki. I'm a malware analyst and forensic investigator as well. We work for Internet Initiative Japan, that is a Japanese ISP. We are the CISA team members of our company. This is the agenda of this presentation. In the first half, we will talk about our motivation and goals, the data structures of the VSS management files, and how VSS works. In the second half, we will explain our tool implementation. We will show you the restoration test results of our tool and some popular tools. Lastly, we will show you two demonstrations of the tools. This presentation is our research on VSS, that is short for Volume Shadow Copy Service. We can create snapshots of NTFS volumes by using the feature. And we can access the past data by referring to the snapshots. In incident response, it is important for responders to access them to find traces of attacks from the snapshots. However, they might be deleted due to the capacity limit or by attacker and malware. In this presentation, we will explain the approach of accessing the deleted snapshots. We will also explain the implementation of our tools. We will also show you two demonstrations, such as recovering data from a machine infected with ransomware. Before we start this talk, let me explain a background of this research. We are incident responders as well. How can we utilize VSS snapshots in incident response? We can find many evidences, such as attackers' tools, archived files created by attackers, deleted event logs, and so on from the snapshots. We use this feature all the time. Thus, the feature is very important for incident responders. Next, let me explain our motivation for this research. Basically, deleted snapshots cannot be accessed with the standard VSS feature on Windows. However, Teru Yamazaki confirmed that a certain tool can access deleted snapshots under certain conditions. Therefore, there is a possibility that data can be recovered. This is the first motivation. Of course, we could use file carving method to restore deleted snapshots data, but it can only recover up to 16 kilobytes of a file or a record in them, because the size of a snapshot data chunk is that value, and chunks might not be sequential. In addition, we have to combining data on the current NTFS volume with data in snapshots to retrieve backed up files correctly. So, whole contents of large files in snapshots might not be restored by this method. In brief, we needed a dedicated tool to access deleted snapshots, but there was no free software. This is the second motivation. Our goal is to create a tool to restore files from deleted snapshots that were automatically deleted due to lack of capacity, or snapshots that were deleted by attackers, ransomware, and so on. Okay, next, we will explain data structures of VSS snapshots in this section. Let's take a look at VSS snapshot management files. A snapshot consists of two kinds of files. One is called the catalog, and another one is called store. They are stored in the system volume information folder that is located directly under the volume root. The catalog manages metadata information of store files, and the store files are stored backup data. The management data of VSS snapshot is existent as files, but the VSS operates on the layer lower than the NTFS. Therefore, when VSS refers to snapshots data, it follows offsets of each management data directly instead of parsing the NTFS file system. Actually, there is further data called VSS volume header beside the catalog and store. VSS volume header is created at the offset 1E00 in hex of the NTFS volume. VSS accesses snapshots by following the offset as in this figure, like this. First, it gets the catalog offset from the VSS volume header at 1E00 in hex here, and then acquires a store offset on the catalog here. Then it can access the store here or here. Next, let's look into each data structure. The VSS volume header has mainly two data fields. They are the VSS identifier and the catalog offset. The head of the catalog and each store data have the same value as the value of the VSS identifier. Therefore, we can use it as a signature for finding them. This figure is a sample of a VSS volume header. You can see the VSS ID and a catalog offset here and here. The catalog consists of the catalog block header and catalog entries. A snapshot is managed by a catalog entry that consists of catalog entry type 2 and 3. And entry type 2 manages metadata information such as a snapshot creation date and time. A type 3 manages offsets of each store block such as a store header offset, a store block list offset, and a store block range offset, and so on. This is a sample of the catalog. You can see the block header here, and a set of catalog entries. And you can also see many data fields. However, since the data format is not very important in this presentation, just remember that there is such data like this. Next, store. Store data consists of 4 kinds of store blocks. The representative data in them is the record type 3 here, which indicate the store block list. It manages a table that has offsets of original data blocks and offsets of backed up data blocks. This is a sample of a store block list. You can see original data block offset, and a backed up data block offset here. Next, let me explain how VSS works. First, how does VSS store data to snapshots? When a snapshot is created, the catalog and a store are allocated. A data chunk to be backed up is managed in 16 kilobytes units called data block. Let's assume these are data blocks. And this file has 3 data blocks here. As an example, let's see how this file that uses 3 data blocks are backed up to snapshots. When a data block in the file has been modified, the block is backed up to store 1 before it is overwritten. In this case, an application has changed the first data block. Then the original data block is backed up to store 1 here. When a second snapshot is created, the VSS adds the second catalog entry to the catalog and allocates a second store. After that, if the application modified the first and second block, they are backed up to the second store, like this and this. And the third or later snapshots will be processed similarly. Next, let's see how VSS access stored data on snapshots. When accessing backed up data of a snapshot, the VSS combines data blocks on the current NTFS volume with data blocks stored in multiple store files to reproduce the data at the time of creating the snapshot. As an example, let's consider a case of accessing a file in snapshot 1. First, the data blocks of the file on the current volume are combined with the data blocks stored in store 2. As a result, we can get this content. Second, the data blocks, which are reconstructed at the previous step, are further combined with the data blocks stored in store 1 to recreate the data at the time of creating store 1, like this. In this way, by combining data blocks on snapshots with data blocks on the current NTFS volume, we can access the data when a snapshot has been created. Next, let's take a look at the behavior of snapshots deletion. All of the snapshots will be deleted if this command is executed. After the command execution, the state of the catalog and the store will be like this figure. We can still see the MFT entries of the deleted catalogs and store. However, the content of the catalog is lost because all of the entry types here and here are changed to 1. And other data filled with 0, like this. On the other hand, although a GUID on the store header is changed, and the other data is still remaining. In addition, the changed data does not affect any operations. After several minutes, the catalog and the store entries will be completely deleted from the MFT several minutes after the command execution. In this figure, although the deleted store file name still exists on the result of FLS command, it is just a $I30 entry. So you will not be able to access store data contents several minutes after snapshot deletion.
Okay, next we will look at the support status of the popular tools for passing VSS snapshots. A lot of software supports VSS snapshots. For example, commercial software such as Forensics Toolkit, X-Ways Forensics, Axiom, and NKS, as well as free software such as Shadow Explorer and ShadowKit. And also open source software such as LibVShadow. There are many tools, but most tools cannot access deleted snapshots. X-Ways can access snapshots if MFT entries of deleted catalog and store are still remaining. However, these MFT entries are eventually deleted. It is not practical. As a result, we decided to adopt the LibVShadow as the base of the tools we created. So, why we did adopt LibVShadow? In our experience, LibVShadow could handle VSS snapshots even when some commercial software could not handle them correctly. VShadow mount command, which reproduces snapshots as a raw disk image, is easy to use with other disk image processing tools. The VSS snapshot parser is implemented without any Windows file system related APIs, unlike other software. In addition, it is open source software. Thus, it is easy to extend the functions. Yeah, and you can download and use it for free. So, this is where we begin with our main issue. We will consider how to restore deleted snapshots. We need to restore store and regenerate catalog to access the deleted snapshot. However, there are following problems for restoring catalog and store. We have 3 problems, like this. So, problem 1, so since the store data is retained in the disk image after deletion, it can be carved from the disk image and the data could be restored. However, since the store consists of 4 types of store blocks, the carved store blocks must be rebuilt into one store. So our solution to problem 1, so we decided to check the positions of store blocks on NTFS volume and consider how the store can be rebuilt. So the offsets of each store block recorded in the catalog entry type 3 resides within a relatively narrow address range. So next, we created a tool to search store blocks in a disk image. The store blocks that we find always appear in the order of record type 4, 3, 5, 6, 6. Therefore, we can consider that it is possible to carve them as a single store. So these blocks are considered as the first store, and these considered as a second store. Next, problem 2. The data of the catalog is completely lost after deletion. Therefore, it is necessary to regenerate it from the carved store. A solution to the problem is like following. A catalog has two main information, snapshot, timestamp, and store offsets. The offsets can be obtained from the carved store, but the snapshot creation date and time are completely lost. We needed to sort the snapshots by the creation date and time to access the data properly. In other words, if the order of the snapshots is correct, the creation date and time can be arbitrary value. And therefore, we decided to set snapshot creation dates based on carved ones. And the last problem, when multiple stores are carved, we cannot identify the order in which they were created. The solution, we assumed that if a new store is corrected, a larger offset of NTFS volume than the existing snapshots will be given. When regenerating catalog data, set the current date as the snapshot creation date for the store with the largest offset. Then we set the timestamp of the snapshot to an hour before the creation date of the following snapshot. However, we practice it is possible that new stores are created with smaller offsets, since we cannot determine the offsets automatically in this situation. We have created a tool to change the order of snapshots. Okay, now we will introduce our tools, overview, and file restoration test. Okay, VSS cover.py carves the stores from a disk image and regenerate a catalog from the carved stores. If there is catalog in a disk image, VSS cover merges with carved information. VSS catalog manipulator.py is a tool for manipulating the catalog entries. This tool can change the order of entries, delete entries, etc. And last, extended VSS mount is a tool for mounting deleted VSS snapshots. We added two new options for reading the restored catalog and the carved store. Okay, this slide is just a usage of VSScover.py, so I will skip it. So please check it later. And skip this one too. Okay, this is an overview of the tool we created. At first, carve the store from disk image by using VSScover.py. Then regenerate the catalog. And finally, extended VShadow mount combines the disk image with other information to access deleted snapshots. We conducted a file restoration test from the following disk images using multiple snapshot parsers. So test for preparation, we prepared files that were 3 kilobyte, 5 megabyte, and 50 megabyte large. For each of them, we put 10 files on the disk, and we created a snapshot. After that, add 1 byte of data to the beginning of each file and save the file. Test 1. So we deleted all snapshots, but the MFT entries still remain. Test 2. We deleted all snapshots and files. Then we copied another 10 files whose size were 5 megabyte and deleted them. We repeated the operation 5 times. Test 3, we executed TeslaCrypt to encrypt files. Since we wanted to run it in a closed environment, so we used TeslaCrypt. It can run without the internet. Okay. So this is the results of the file resolution test. So with commercial software A, we could restore all of the files of test 1. But we couldn't restore any files other tests. In addition, with other software, commercial software B and free software C, and software A version Z. So we also couldn't restore any files. On the other hand, our tools could restore all of the files, all of the tests. Okay, let's demonstrate our tools. We will show you 2 demonstration movies. The first demonstration is a file restoration from a deleted snapshot of Windows 7 disk image. The snapshot was deleted because it was over the upper limit of VSS capacity. Okay. We prepared a Windows 7 disk image which was operated for a month. There are 3 snapshots in the disk image. However, we have been able to find one more snapshot when we used VSS cover.py. It means that we could recover data that is older than the data of the existing snapshots. Okay. Okay. At first, mount a disk image to analyze. Okay, after mounting, confirm partition table in it. There is a Windows partition at sector 206848. Next, confirm VSS snapshots information. So there are 3 VSS snapshots. Then execute VSS cover.py. First of all, this process. Yeah, listing recovered snapshots. Yeah, now we can see one recovered snapshot, that red box. Then mount the recovered snapshot with extended V shadow mount. Now let's make sure that how many snapshots were mounted. We can see 4 snapshots. VSS1 is a recovered snapshot. Other snapshots were converted from an existing catalog in the disk image. Export system.evtx from VSS1 and VSS2, then compare each latest event log entry. Identify MFT record number of system EVTX in VSS1. The MFT record number is 44566. Check also in VSS2. It's the same number. So export system.evtx from VSS1. And next, export it from VSS2. Now we can see two system EVTX files. Okay, open these files.
Sorry for Japanese environment.
Okay, so the latest system event log entry in VSS1 is recorded on June 30th, 2017. On the other hand, the latest one in VSS2 is recorded on July 13th, 2017. Therefore, we could confirm that the curved VSS snapshot is the oldest snapshot. That is all, demo one. Okay, region presentation. Okay, the next demonstration, second demonstration is file restoration from a snapshot that was deleted by TeslaCrypt. It is ransomware. The upper half of the screen shows operations on the victim computer, and the lower half shows operations on the analysis computer. Yeah, we will operate on a victim PC at first. There is no VSS snapshot in the victim PC. Create a VSS snapshot by executing wmic.exe. And there are two document files, docx file and Python script in the documents folder. Edit the docx file. Okay. And then save this file. Next, edit the Python script too. Oh, very slow. Okay, then save this file. Okay, now there is one VSS snapshot and its size is 3.31 megabyte. So let's execute TeslaScript. So TeslaScript is encrypting targeted files now. So the document files have been encrypted. Okay, so TeslaScript has been completed to encrypt all targeted files. And all snapshots have been deleted by TeslaScript. So acquire a disk image of the victim PC. Next, operates on analysis PC. Then mount the disk image on the analysis PC. Execute the VMDK mount to mount the disk image. Execute MMLS to identify a partition table. Windows partition starts from sector 1026048. So make sure the VSS snapshot status. So execute, there is no snapshots because TeslaScript deleted all of them. Okay, so execute vsscover.py. Okay, fast forward this process. Then listing recovered snapshots. Okay, VSS cover has recovered one VSS snapshot. Okay, mount the disk image of victim computer with the recovered catalog and store. And check MFT record number for documents folder on the victim PC to export the recovered files. Okay, the MFT record number is 95941. and execute FLS to list MFT record numbers and file names under the documents folder. Yeah, now we can see example docx and VSS cover.py. And then export example docx. Yeah, export VSS cover.py too. Okay, make sure contents of exported files. Okay, finally, we were able to recover the files. Okay. And now I want to talk about scope snapshots because it is one of the very important parameter of VSS. Since Windows 8, scope snapshots is enabled by default. If the feature is enabled, only system files are backed up to VSS snapshot. Other data cannot be backed up. To disable this setting, change the following registry value and reboot the computer. Okay, this registry key and values. For details, check our report on scope snapshots. Okay, we have planned to improve our tools. So expanding the support to the extended vShadow mount command into Linux and macOS. Following the latest source code of vShadow and implementing identification of snapshot creation dates of the recovered store. Implementing automatic sort by store creation date and time. Okay, conclusion. VSS cover.py can restore catalog and store data from a disk image. In addition, extended vShadow mount offers the feature to access deleted VSS snapshots with the restored catalog and store data. We also confirmed that VSS cover.py is effective for snapshots that were deleted by a system or ransomware. Okay, these tools are released already. Okay, thank you for your attention. Do you have any questions? Okay. Do you have any questions?
Can you go back one slide?
Okay. This slide?
Yes.
Yeah.
If you have questions, please move to the mic to the aisle that you can ask.
I have a question. For the ransomware example, if you waited an hour or 2 hours after the ransomware encrypted the files, would you still be able to recover the deleted snapshots?
Yeah, it could be, but it depends on the environment, but and the ransomware. But it could be because if the snapshot data haven't overwritten, the data still remain, and if we can curve, then we can recover it.
Thank you.
Hi. I just have a question about the, so you're assuming attacker just used this executable to delete the VSS. What if the attacker, instead of using the tool, but using, directly accessing the disk to randomly write those, data blocks that VSS owns and randomly write any arbitrary things?
Yeah,
Are
yeah.
you still able to recover VSS?
In that case, we have no, we have no choice. We cannot recover that data because allocated space doesn't have any store data, so we cannot in that case.
I have a question. In your experience, have you seen any ransomware that you cannot recover the shadow copy of the data? In your experience?
Yeah, I'm not sure, but I heard that only ransomware. Someone said the tool couldn't recover the data from only ransomware, but I'm not sure I'm not sure the reason why the tool cannot recover the data. But in theory, it could recover the data if the store data remain on unallocated spaces.
Okay, thank you.
Okay. Anyone? Okay. Thank you for attending our session.